Okay, so welcome everybody to the seminar today, and we will have Subir Sachdev telling us about his own eponymous model and how it has revolutionized our understanding of non-Fermi liquids and also black holes. And so there's no better introduction I can give. So over to Subir.
Okay, thank you very much, Ayan. It's great to be at IIT Madras virtually. As I was just telling Ayan, I think the last time I actually was on the campus was, 1977, when I was a high school student in Bangalore, in Kendriya Vidyalaya, and I came to IIT Madras to play table tennis. Well, hopefully next time I can come to discuss physics. But anyway, all right, so I'm going to talk about the SYK model and some applications to black holes and non-Fermi liquids. So let me just begin right away with just a summary of some basic properties of SYK models. By the way, please feel free to interrupt anytime with questions. So let me begin with a much simpler model and a much older model, which is just essentially the random matrix model. We have here fermions hopping between n sites, and any fermion can hop to any other site with the matrix elements Tij. And Tij is a random number with zero mean. And the other important property, in fact, is that all of the they're independent random numbers. The distribution doesn't matter in the large n limit. So what's known, for example, that if you look at the eigenvalues of a random matrix, you get the famous semicircular density of states. For finite n, you actually have a discrete set of eigenvalues with spacing 1 over n. But here I want to think of this as a many-body system, not just as a single matrix, where you're occupying fermions. And then depending on the chemical potential, you will occupy all states below the chemical potential. And this would be what we call the Fermi energy. So there's a density of states at the Fermi energy, which is some number rho naught. And then the specific heat, for example, and the entropy at low temperature has this famous Sommerfeld form. It's proportional to the number of electrons, is proportional to temperature, and this coefficient we call gamma in condensed matter physics, the gamma coefficient. And for this case, it's just related to the density of states. Okay, so now let me just still talk about this same model, but think of it as a many-body system. And so in a many-body system, we're going to plot the many-body density of states. So here, E sub I is the sum of all the energies of all the occupied states. So the total number of states, E sub I, in the grand canonical ensemble is 2 to the n. So not n, but 2 to the n. And this is the density of those 2 to the n states. So now you can, for example, we'll focus on the lower energy region. This is a zoom of the lower energy region. And this is just the discrete eigenvalues at the very bottom of the band. If you look at a region where the energy is extensive, which is presumably somewhere here at low energies, then of course the many-body density of states is just the exponential of the entropy. Now the entropy I just told you was this in the canonical ensemble. It takes a few lines to just convert it to the entropy in the microcanonical ensemble, and you get this answer here. And notice, of course, that when the energy is extensive, this is E to the n. I mean, as it has to be because the total number of states is so large. So that's the density of states when the energy is extensive. Now you can ask what happens right near the bottom of the many-body band. And here the spacing is much smaller, or much larger, excuse me. It's of order 1 over n. And the reason the spacing here is 1 over n is because the spacing of these levels is 1 over n. So at low energies, all you're doing is moving particles from occupied states to empty states down here. And that gives constant energy of order 1 over n. And so the space density of states is not exponentially large as it's here, but it's in fact proportional to n. When the energy is of order 1 over n, the density of states is of order n. All right, so so that's a quick review of a very familiar model. So now let's go directly to the SYK model. It has a very similar structure, except instead of having a 2 fermion term, you have a 4 fermion term. And so this U is an interaction matrix element between n possible states. And there are of order n to the 4th such interaction matrix elements. And again, the main assumption is these are independent random numbers. Of course, in any real system, these have some fixed value, if at all you can describe it this way. But then the problem is completely impossible to solve because, again, the Hilbert space now is 2 to the n. But remarkably, when you assume they're independent random numbers, you can solve it in the large n limit. And moreover, we now know that this system is extremely strongly self-averaging, so that you just need one sample, and it just self-averages to the average value in the large n limit. So here's the same quantity, the density of states, the Manybody density of states. And now you notice it looks very different. It doesn't have those tails. It seems much more regular at all energies. And what is the main difference? Well, it's already apparent when you look at energies which are extensive. And there, what was shown first in this paper, that this model at low temperatures has an extensive 0 temperature entropy. And now, at first that might seem very shocking because it implies a huge ground state degeneracy, but it's not a ground state degeneracy. But so I'll come to that in a minute when we look at what happens near the ground state. But the entropy now, instead of being just n gamma t, it is still linear in temperature. There's an offset, which is also extensive. So if you now go from this canonical result to the microcanonical result, you get this value here. And that actually agrees very well with the numerical data. However, the effect of the 0 temperature entropy becomes more dramatic right down at the bottom of the band. And there, it's known today that the density of states looks like this. This is the energies of order 1 over n. So this is just a constant. But there is a prefactor, which is exponentially large. So the density of states, instead of being of order n, as it for a system of free fermions, it's now of order e to the n, even at the bottom of the band. And the reason it's about e to the n is not because of a degeneracy. You can see there's no degeneracy here at all. It's because the level spacing remains exponentially small, even close to the ground state. And this immediately means that there is no single particle description of these states. If you had quasi-particles, the number of quasi-particles are of order n, not of order e to the n, and there's not enough quasi-particles to give you so many low energy excitations. So that's really, as a net matter, that's one of the most interesting features of this model is the absence of quasi-particles and still gives you a solvable description. We know today, and I'll give you, yes.
Can I ask a question? So in the first slide, you said about random matrices. So this is not describable in terms of random matrices in this, at least in this way. This spectrum can be understood as some kind of matrix ensemble?
Okay, so yeah, that's a good question. So let me clarify. So first of all, this is these U alpha, beta, gamma, delta are random numbers, but the number of independent random numbers is n to the 4th. Okay, because there's 4 indices. On the other hand, if I think of this Hamiltonian as a matrix, it's a 2 to the n by 2 to the n matrix. It's a huge matrix. So the number of matrix elements is 2 to the 2n. And so it's a highly correlated matrix. It's mostly 0 because you're filling that huge matrix by n to the 4th numbers. So that's, in that sense, it's not a fully random matrix. It's really a matrix only in this set of Fock space matrix elements, random, these are n to the 4th random matrix elements. But nevertheless, there's a certain idea of random matrix universality. So you can ask, so if you want to get all of these results, they don't come out of an arbitrary random matrix. They come out of this particular model. But you can ask a different set of questions. What is the statistics of the spacing between these levels? And that's a much finer question at the very small energy level spacing. So there's no proof of that, but there's a lot of evidence, especially in the work by Steve Shenker and his collaborators, that the energy level spacing here does obey random matrix statistics. And you know, so that comes also has been proven for the case for the JT gravity recently, but JT gravity is not completely the SYK model, because, but we generally believe that it's true, that if you look at the distribution of energy level spacings, you will still have random matrix, the universal Wigner-Dyson random matrix behavior.
So this evidence is from this partition function at beta plus some IT, some where complex. So you put some real time. This mod z.
Yeah. So
this partition function square.
For example. Yeah.
I
So
see.
they get what they call the ramp, right? So
the ramp there.
So
yes.
the ramp is some kind of Fourier transform of the level repulsion. Now, yes. For the SYK model, no one has really proven that the ramp is present. There's numerical evidence for it. For the JT gravity, which is a low energy approximation to SYK model, it's basically been proven. But that's okay. That's maybe a fine point, but an important distinction. It hasn't really been proven for the SYK model, as far as I know.
Thank you.
But I'm not focusing on, you know, the ramp again is a very, very long time behavior. I'm not focusing on that at all. I'm talking about things at earlier times, where you know, which is give you where we're just interested in the coarse grain density of states. But coarse grains are for, you know, over a very small energy interval of e to the minus n. Also, and I'll give some indication of where this comes from, there's also an exact interpolation function known between these two limits, each of, you know, this, and it's this cinch function. And when you go to the canonical ensemble, it gives you a correction to the entropy, a 1/n correction to the entropy, which is this minus 3/2 log 1/t. And this cinch function is what also comes out of JT gravity. Okay, I'll give some indication of that in a few minutes. All right, so that's a summary of, you know, just numerical results on the SYK model, and contrasting this density of states with this density of states for the for the random, you know, n by n random matrix, where there are these tails, and these tails represent the fact that density is much smaller at low energies, which is consequence of the existence of quasi-particles. All right, so let me give you now just some summary of where these results come from, and also mention a few other results that we are interested in. So the simplest way to obtain, at least to start the analysis, is just do Feynman graph expansion. Just expand the powers of the interaction, and then average graph by graph. And if you do this, you get these very simple looking equations for the Fermion-Green's function, where the self energy is basically G cubed. This is the so now called a Mellon graph. So when we first wrote down these equations, we thought, oh, well, we'll figure out what's going on in these equations in a few months. But this is an amazingly rich set of equations, and we're still learning new things about them, which I'll mention in a few minutes. All right, but what we did figure out already in '93 was that the long time solution of these equations is, at least at the particle hole symmetric point, we also had the non-zero mu case, is 1/square root of tau. And now this is very well understood to be, you know, just the first signal of a conformally invariant structure with SL2R symmetry. So one of the questions you can ask then, also very now, you know, simple to work out, is what are the corrections to this? So the way you can think about this is in kind of a bootstrap point of view to do conformal perturbation theory. You imagine that your low energy action is the conformal conformal action plus some perturbations. And here O sub H is any set of operators that has a full symmetry, which is basically nothing here other than time reversal. So this is some set of bosonic operators, and G sub H are some coupling constant. And H refers to the scaling dimension where these operators decay as 1/2 to the H. So question you can ask is, what are the possible values of H? And in the large N limit, again, you can show by diagrams, you can try to compute a 3-point correlation function between O sub H and 2 fermions. And this 3-point correlation function in the large N limit is just given by the solution of this integral equation. All right, so now you want a solution which has this divergent behavior as tau goes to 0. And in that limit, you can ignore the bare term and just look at this as an eigenvalue equation where I put an eigenvalue E. And so you have to solve this equation. It's an integral equation with some operator corresponding to these graphs. And you just have to solve this equation and look for values of H for which there's an eigenvalue E equals 1. So when you do this, you find that you get, this was done by, I think, Kolchinsky and what's his name? Vladimir Rosenhaus first. You get infinite tower of states, lots of values of H, which are actually irrational, except for the lowest one. And the lowest one is H equals 2. And this will turn out what's the analog of the stress energy tensor here, which I'll indicate is sometimes called the boundary graviton for good reason. It has dimension 2. So this tells you that the correction to the 1/√of tau in the solution of these equations, we're just solving this equation in some conformally invariant way, in conformal perturbation theory. The correction to this solution we had in '93 was not figured out until recently. The correction is this leading term 1/tau, which comes from the H equals 2 correction.
Can I ask?
The fact it's 1/tau just depends on the fact that this is 2. You can easily figure out. Yes, please.
Yeah, so I'm slightly confused. Maybe it's a stupid question, but so the results that you got in '93 was a large N sort of result, right? So what
this is also large N.
So this is
also large.
This is a first correction in terms of 1/n or something like that. This CGH.
Okay, so there are 2 parameters to keep in mind.
Okay.
One is N, which we have set to infinity. But another parameter is for example, it's sometimes called 1/βj, or it's my language is T over U. You have an energy scale U, and there's temperature, which is our time, or U times tau. So this is the long time limit at N equals infinity.
Mm-hmm.
We are still at N equals infinity. This equation has the N's cancel out completely. This is an equation at N equals infinity. But we're looking at leading 1/βj corrections or T over U corrections. And this is the first T over U correction.
Okay.
So we're still at N equals infinity. We'll shortly go beyond N equals infinity. All right, so in fact, but that's a good point to mention. This is, at N equals infinity, you can work this out by this kind of very perturbative argument. But if you want to figure out the 1/n corrections, it turns out that those are highly singular and they're dominated by this H equal 2 operator. That's the graviton operator. And for that, you need a much more sophisticated non-perturbative analysis, which I will mention in a minute.
So Subir, the claim is that in this eigenvalue equation, only certain value of H can contribute, and H is equal to 2 is the lowest one. Do you know what should be the subleading ones? What subleading H can contribute to this?
I will show it to you. Absolutely, I will show you. There's a finite discrete set of H for which E equals 1. Okay, you have to put E equals 1 because there wasn't an E to begin with. Okay, so let me just, and the next one is something like 3.77. I'll show it to you in a minute. Yeah.
Oh, okay. I see. Sorry.
In fact, and then they're all irrational numbers. So in fact, here it is right there. It's 3.773354. Anyway,
but
so
Subir, in that case, do we understand why h is equal to 2? Is there some good reason to understand why it is h is equal to 2 here? Why the lowest value is rational and why it is 2?
yes, yes. So this h turns out to be precisely the time reparameterization operator.
Ah, okay.
Well, we'll come to
Thank
that.
you.
Yeah, this
Okay.
is so there is a. It's it's very similar to in conformal field theories. You have the stress energy tensor, which is in dimension 2, and you have the currents, which have dimension 1. But then all the other operators in a CFT in 2 dimensions, well, they have rational scaling dimensions, which are determined by, who knows, very complicated equations. But there's a universal set of operators like the stress energy tensor and the current, which have simple dimensions. Here it's similar, except that first of all, the set of H is not finite, it's infinite, and it's not rational. So this is not a rational conformal field theory. It's infinite and irrational, but this special operator remains exactly fixed.
Thank you.
And that's even true in higher dimensions. If you take ON model in 3 dimensions, again, there are some simple operators which are simple scaling dimensions, which are just integers, and then there's an infinite set of irrational operators. So in some sense, the SYK model has this kind of, I would say, magical property that it's solvable, but it's more like higher dimensional CFTs, which have all these strange properties, which have these irrational scaling dimensions with infinite number of operators. So it's like this golden mean of complexity and solvability. Okay.
Let's see.
So for example, one of the things that at least for us for physical applications is to compute the spin susceptibility. This is basically, oops, I wrote it down somewhere. Oh, I erased that slide. Sorry, I have to make a correction. So this chi of tau is g of tau, g of minus tau. Anyway, so you could take this result for g of tau and take a Fourier transform and then multiply by g of minus tau and so on. And you can reconstruct what we call the spin susceptibility. And this is the series exactly at n equals infinity that we worked out. These numbers C is a known number, and gamma is the same as the gamma in the specific heat. So this is the contribution of the H equals 2 operator. This is the H equals 2 operator squared. This is the first correction, which comes from the H equals 3.77354 and so on. This is the H equals 2 operator cubed. And this beautifully fits the numerical data when you solve the SY equations. And this linear dependence here, this term is the boundary graviton. Okay. We can also do this at finite temperature. And if we just take the first 2 terms, the leading term, which is sine omega, becomes tanh. And this is a consequence of the conformal invariance, first noted by Georges and Parcolet. And what is very exciting about this observation is that the natural frequency scale is temperature, and it's totally independent of U. These days, it's sometimes called the Planckian dissipation. And then the correction also has a universal dependence that you can work out. That's the boundary graviton. Okay, so what I've told you so far is just our current understanding of just the solution at n equals infinity of the SYK model. And as you can see from this kind of series, it's now very well understood. So now we want to think about 1/n corrections, fluctuations about the saddle point.
Subir, can I ask?
And these turn out.
Can I ask
Yes,
a very quick question? Sorry. So the numerics that you did, what sort of numerics is this?
It's just the numerical solution of these equations.
Oh, it's just a numeric. Okay. Thanks. Okay.
In fact, this tells you how I've been stuck on the same problem for so many years. This red line was already in my first paper in 1993.
Right.
And it's taken so many years to now get an analytical understanding of it.
Okay.
Okay, so now we want to look at 1/n corrections. And this is where, people like Maldacena, Kitev, and Polchinski, Rosenhaus, Gross, Stanford have made very important contributions. And I'll summarize their and others' contribution. So it turns out that the 1/n fluctuations about the saddle point are dominated by this h = 2 operator. And we need to really take into account non-perturbatively. All other operators seem to be much better behaved. And I'll try to give you some indication of why that happens. Okay, so if you take the original Hamiltonian and average it, then this is the average partition function. I've introduced some replica indices, but we just drop them from now on. And then you just insert this trivial identity here, because if you just integrate over sigma, you get a delta function of g, and then you integrate over g, so that gives you 1. But this imposes the fact that g is in fact the Green's function of C and C dagger. And so once you insert this in here, and then you can do some rearrangement and integrate out the fermions, and so you end up with an formally exact representation of the average partition function, which is now an integral over just 2 fields, which are bilocal in time, sometimes called the DSigma theory. And this is the form of the action. It's got this log det term and so on. All right. So this is actually secretly some sort of theory of gravity. And why that is something you can see by noticing this following very important observation. The point is that when you take the low energy limit to get this 1/square root of tau solution, that's the saddle point of this action. And in that saddle point, this term doesn't matter at all. This is the term that gives you all the corrections I was just talking about at n = infinity. So if you just throw out that term, then the remaining action turns out to have a huge amount of symmetry. In particular, it has a time reparamerization symmetry, hence the connections to gravity. You reparameterize from time tau to sigma, and the new action in terms of g tildes and sigma tildes has the same form as the original action. It just takes a few lines to check that. There's also a gauge symmetry, which I just won't talk about, which is important for some things. All right. However, this is an approximate symmetry because there is this term which definitely breaks this symmetry. So however, that term is less important because at low energies we know it totally disappears. So the strategy is following. If you ignore this term, then as you're doing the path integral over g and sigma, there's one direction in g sigma space where the action is flat. It doesn't change at all because the action remains invariant under this transformation. So what you want to do is do this path integral along that flat direction. It's not really flat because this term is not exactly 0. So what is that flat direction? Well, the flat direction is in G space is this. You take the saddle point solution, G sub S, which I just described, and you perform a time reparameterization of it. Okay, so this G of tau 1, tau 2 only depends on F of tau via this saddle point reparameterization, the time reparameterization of the saddle point solution. There's also a gauge transformation, but I won't mention that. And so what you've done is taken the saddle point solutions and made some corrections to it if F of tau is close to unity. And those corrections, the leading correction of this saddle point is in fact a time reparameterization correction. And to answer an earlier question, that's precisely what gives you this operator O sub H here, if you work it out with H = 2. Okay, so this, where did it go? Yeah, so this correction, which comes from H = 2, is precisely the correction that you get from this by just going along the flat direction in action space, in G sigma space. All right, but it's not really flat. So there's some action. S is not independent of F. It depends on F. And so you have to figure out how does the action depend on F. And you can reduce everything from this integral to just an ordinary functional integral of just a single, it's just or looks like quantum mechanics, just one time coordinate, and with some action. Okay, and that action can be deduced a variety of ways, generally using symmetries and various other arguments. It has two terms. One is for the gauge symmetry, and that has the action of a rotor. And this is basically sort of like the Coulomb blockade term. It's just telling you that the total charge on the dot can fluctuate on this model. But the more interesting term is this term here, the so-called Schwarzschian of f of tau, and its coefficient is the specific heat coefficient gamma. So this gamma, so this term here is intimately connected to the OH equals the full nonlinear action for time parameterization fluctuation or the operator with H equals 2. All right, and amazingly, this path integral with this action, even though the action looks so horribly complicated, it can be performed exactly due to some remarkable identities using the SL2R symmetry of the saddle point, which I won't talk about. Anyway, so you can, from this action, you can compute the path integral and hence the density of states. And that's how you get this e to the S0 sinh density of states I mentioned earlier. It comes from this path integral of the Schwarzschian theory. Okay, and this whole theory is just determined by one coupling constant, which is gamma, which depends on the microscopic UV structure. It's not something we can compute exactly. You have to just determine it numerically. But once you figure out what gamma is, there's a whole host of corrections that you can get, including the density of states where the gamma appears, and even this alpha G is related by some constant to gamma. Okay, right. So that's basically a quick summary of much of what we know about the SYK model. Any further questions before I move on to other topics?
A very simple question. Actually, this gamma is related to this the module square divergence, or what determines gamma in the original SYK? From the original SYK point of view?
It's something you just it has dimensions of 1 over energy, so it's basically 1 over u. So or if you're doing this for a black hole, it would be 1 over the Planck mass or something like that, as I'm going to do in a minute, as you'll see.
Okay.
So it's just something it depends on the UV structure. So it's hard. It's not something we know. Suppose I took this original Hamiltonian. Sorry, oops, that's a long way back. If I took this Hamiltonian, I added other terms. I can add a 6 fermion term or 8 fermion term. Now those are irrelevant operators in the UV physics, and they will not change any of the results I've talked about. All of that will be the same, but they will change the value of gamma. So gamma is whatever it is. It's like a low energy. It's the single parameter characterizing the low energy physics, but it's not something we know accurately, except by numerics.
Yeah, just another question is, so normally if you say that, if you believe this is somehow, it's dual to some kind of string theory, this SYK, then it has to have this strange kind of irrational H, right? Which is a little bit, I mean, there's no such known,
right.
Theory which
Correct.
has this kind of a spectrum.
I'm not saying, I agree. So the statement is that the SYK model is a UV complete theory. Okay, it's perfectly well defined on its own, and its low energy theory of the SYK model coincides with 2D gravity on ADS2. Okay, now you can certainly embed 2D gravity on ADS2 in string theory, but that's a different UV completion. Okay, these are two different UV completions of the same low energy theory. Okay. So now, this low energy, this 2D gravity theory doesn't know anything about all those irrational scaling dimensions. The irrational scaling operators are only properties of the SYK model. They're not a property of JT gravity. Okay, they're not included in JT gravity at all. So, so at least in my naive point of view, it seems like it's not a very meaningful question to ask. What is the string theory equivalent of SYK? SYK is already UV complete. It is what it is. It's its own theory. It's completely UV complete. Why should you bother to put it in string theory, which is a different UV completion?
Yeah, that's right. Yeah, but it might be a good example where one can look for a kind of exact quantum gravity dual, perhaps, and that's probably the motivation. But what I want to also ask is
what do you mean by a theory of quantum gravity? I mean, you know, if by theory of quantum gravity you mean path integral over Einstein gravity, then we know that's not well defined. So what is a quantum theory of gravity?
Stringy modes, perhaps included.
Yeah, but a quantum theory of gravity is any theory. A quantum theory of gravity is any theory whose low energy theory is Einstein gravity. And in that sense, SYK is a quantum theory of gravity because there's a limit in which its low energy theory is some very peculiar kind of gravity. Okay, sorry. Sorry for that rant.
Yeah. But what I actually wanted to ask was this, that you have this sort of conformal perturbation theory now with this undefined coefficients that you can add, right? And is there some, and there is a specific kind of the thing that leads to, you need a whole tower of it and which leads to some UV completion, right? So is there a way to study by bootstrap, like what are generalizations of this in the sense of, is there some other analogs of SYK with the same low energy limit but different UV completion? Is there some bootstrap way of understanding this?
Okay, there's a number of questions. So first of all, I just mentioned other UV completion. You could take SYK with the Q equals 4 term and add arbitrary Q equals 6 term. That's a another UV completion of the same theory. It'll have the same values of H, the same tower of operators. No, but even in general conformal field theory, every time you have a new anomalous dimension, you have an operator with an anomalous dimension. Every operator with an anomalous dimension comes with a non-universal amplitude. There's a normalization constant associated with it. Now, typically, you know, you just normalize it so the 2-point correlation function is 1. And you forget about that normalization, but it's always there anytime you consider CFT as a low energy theory of some lattice UV complete model. And figuring out the normalizations of all the operators is not an easy task. It just depends. It's not something Bootstrap even begins to address because it's a property of the UV completion, not a property of the CFT. You know, when you're doing Bootstrap, you define your operators so that this coefficient here is 1. That's implicitly done in Bootstrap. But if you have a UV complete theory, it's not 1, it's something else. And but that whatever it is depends entirely on the full structure of the UV completion.
No, by Bootstrap here, I also meant these 3-point functions which are affecting your computation. Yeah. So in that way,
right. So the 3-point, that's universal. Of course, that we can compute. That's all known. Yeah, that's the kind of thing that Rosenhaus and Gross have computed. So that's a relationship between the three. That's a relationship between the prefactor of the 2-point correlator and the 3-point correlator. That's universal. But this G sub H is not, you know, I mean, I should put an equal to time here. If I put this equal to 1, then the G sub H is unknown. If I have too many unknowns here. Either I can make G sub H variable or I can make the normalization variable. Yeah.
Okay, thanks.
Yeah, okay.
Hi, I have a question.
All right, so
I have a question. Please. So from that effective action you had on the slide, what's the quickest way to say this? See this S0 term.
The S0 term. That's not part of this actually. Yeah, so that's.
How do I make out there's a S0 is a way to see it?
No, that's not. That doesn't. The S0 is just a constant in front of this. It's just an extra constant. So this effective action, if I go back to the entropy here, you know, Yeah, so the effective action gives you the gamma T term. It doesn't give you the S0. So the S0 from the gravity point of view is just an arbitrary constant. For the SYK model, it's a very specific number. For this particular UV completion, it's this number. And it's also universal. And it somehow knows about, about all the irrational operators. And so, maybe there's some string theory that gives the same number, but I would say I don't understand that very well either. That's an excellent question. This number S0 has a degree of universality that it's something we can get universally from the SYK model. It doesn't depend on a lot of details. But at the same time, do I know of other models that have the same S0? No, I don't.
But I thought you had an expression for the D of E calculated from the effective action.
That
right?
gives you this term here. That gives you the cinch. It gives you
But
the cinch.
you don't still get the small S0 part.
That's just a prefactor in front of everything. And it is, but it's the same. Yeah, the S0 is really very crucial. And in fact, in the cinch, one of the places computed first was a Witten and Stanford paper. They don't even write this prefactor, which I thought was very confusing because in fact, that's the most important term here. This is just a correction to that. Anyway, okay.
So even if you're looking for the 1/n corrections or something, you don't see this S0 part like as a scaling factor or something?
No, the S0 part is already present in the n equals infinity theory. It was worked out here in 2001. We were just working at n equals infinity, you see the S0 part. And you could also see this.
But in the 1/n corrections from the rest of it would combine with the NS0 terms, right? Or is that?
It just comes as an overall prefactor. That's all. You can see the S0 just an overall prefactor everywhere. And this term here, which is also of order n, when E is of order n, that in principle, we could have figured it out in 2001, but we didn't. We just didn't work hard enough to work it out. And it's quite tricky to get the linear and temperature correction to the free energy of the saddle point. So everything here is in fact at n equals infinity. What's non-perturbative is when you go from E to the square root of this to the cinch of that. So that you can see is highly non-perturbative because there's a term of order E to the n, and there's a term of order E to the minus n inside the cinch. The E to the minus n term is the one that's non-perturbative and that the Schwarzschild gives you. So this factor here is not highly non-perturbative because the square root here depends on the cinch. So amazingly, the Schwarzschild gives you corrections of order E to the minus n. It's amazingly accurate. And it gives you the most important corrections of E to the minus n. And you can also see this here. If you look at this correction, it blows up as temperature goes to 0, but the temperatures have to be about E to the minus n before it's about the leading term. Now, this doesn't mean that there's some instability. It just means that the energy levels become discrete when temperature is about E to the minus n.
I see. And a related question: do we know how S0 changes when there are higher fermion terms and so on, at least numerically?
Yes. So it depends on the smallest non-zero fermion term. So if you have only Q equals 4, then it's this number. If it's Q equals 6, it's some other number. But if you have both Q equals 4 and Q equals 6, it'll be the Q equals 4 number.
Okay.
The Q equals 6 won't matter. Yeah. Okay. All right, great. So now let me give you a little bit of the gravity point of view. This is just a curious thing I just saw in TRL recently, where people have measured from the LIGO observations the typical merger time or ring down time of black holes. And that's also about our h bar over kt, this Planckian time as we call it. This is not to say there are quantum effects here, is because the h bar and the Hawking temperature cancels the h bar here. But it gives you some idea that there is some at least a possibility of a connection between black holes and the SYK model. And this kind of thing was very much in my mind when I proposed this connection in 2010. Okay. All right. So let's just think about thermodynamics of quantum black holes. So the most naive thing you'd want to do is just evaluate this path integral of Einstein gravity in a black hole background. But of course, it doesn't make any sense because we know the path integral is full of UV divergences. But nevertheless, in a very inspiring calculation in 1977, Gibbons and Hawking said, well, let's not worry about all the fluctuation corrections. Somehow they'll be fixed up, and just evaluate this at the saddle point. And they took the saddle point in Euclidean time, and where h bar over kt was the length of the thermal circle. And this is, in fact, the only place that h bar and t appear in the calculation, just from the length of the Euclidean time circle. And so then if you just evaluate the saddle point action for a black hole, you get this famous Beckenstein-Hawking result, which is A over 4 in the usual units of the black hole entropy. And the interpretation of the area dependence, of course, is that this should be viewed as an entanglement entropy between the inside and outside of a black hole. Okay. Now, in fact, Gibbons and Hawking also considered the case of a charged black hole. You take a net charged black hole. So now this is an integral over Maxwell and Einstein. And if you do the same calculation, and you take what's called the extremal limit, in this case, it's a very simple limit where the Hawking temperature goes to 0 at fixed charge Q. And then it turns out that you can write the Beckenstein-Hawking entropy in this form. Well, it's been in the literature for the longest time. Only recently I wrote it down in this form. So this is the 0 temperature result, and then there's a correction that's linear in temperature. Okay. And so this, of course, it should be very suggestive. I just told you that at n equals infinity, the SYK model is S0 plus gamma t, and this seems to have exactly the same temperature dependence here. So knowing this, a sufficiently clever person already, and there's no reason already in 1978, you couldn't have worked out something, understood where this linear temperature came from, and then worked out something about the corrections. So that was not done until very recently, but really when we had the example of the SYK model available. But at this point, all we're just doing is an extension of what Gibbons and Hawking doing, which is the idea that let's just not worry about the UV corrections and just evaluate it in some kind of saddle point expansion. And what we know today is that, of course, this is a correct result. And another way to say it is that this, even though you need some UV completion of this theory, the Beckenstein-Hawking result is kind of a coarse-grained count of the entropy of the low energy states. And it's insensitive to the UV completion. Okay, so what I'm going to claim, yes, please, since I'm not a black hole physicist.
Sorry, but in this case, the residual entropy piece, which is the leading area law, is already apparent from the action, right? You get the area.
This is just the Beckenstein-Hawking result. I've just rewritten it.
Right.
Yes.
In our SYK case, the analog of this one would go to the S0, right? But apparently the S0 you said is not directly deducible from that effective action. Is that right? Right.
So now I'm doing something different. I'm just doing quantum gravity. Forget about SYK for the minute. I'm just doing quantum gravity. And I'm imagining, let's imagine this is embedded in some string theory. Okay. And I'm taking the low energy limit. So in the low energy limit for a non-supersymmetric charged black hole, this is what you'll find from the saddle point. This result could have been deduced directly from Gibbons-Hawking. The fact there's a temperature dependent correction is simply the statement that as you raise the temperature, the area increases. This whole thing is just the area as a function of temperature. maybe I should write that out explicitly. So this is A of T C cubed over 4GH bar, which I write in terms of the area at the 0 temperature. Yeah, I will clarify this in the next version.
Right, but yeah, naively, if you take the analogy, like, shouldn't you be able to see the S0 term from JT gravity or something? Like,
so in the JT gravity, yeah, it's just depends on the cosmological constant. I mean, it's just a constant that depends on what, right? Exactly. So that's it. I will come. Just wait two transparencies, and I'll show you how that happened. So here, that's right. So the S0 term is fully determined here by the UV theory, which, as far as the JT gravity is concerned, the UV theory is Max Einstein gravity in 3 dimensions, 3 + 1 dimensions. Okay, I'll come to that. Okay, that's precisely the next slide, next 2 slides. So if I take a full solution of Einstein-Maxwell theory in the presence of a charged black hole, that's the Reisner-Nordstrom solution. It has the following structure. Near the horizon, there's a 2-dimensional section that's most important, which has ADS2 metric. And there's an S2 part, which we just ignore because it doesn't affect the low temperature behavior. So at low energies, you have 2D gravity. Then there's some boundary layer, and then you go to 4D gravity. Okay, so to define the, so now what we want to do is to start from the 4D gravity, which is a perfectly well-defined theory, at least at the saddle point level, and take its low energy limit and deduce some effective action for 2D gravity. Okay, so that's what we're going to do. So we're going to start from 3 + 1 dimensional gravity and reduce it to 2D gravity. This turns out to be JT gravity. And here, to answer your question, you get the S0 term. You get JT gravity plus the S0 term, and the S0 term is here. Okay, so actually this term, yeah. So you get it. And it's a property of the parent 3 + 1 dimensional theory, which is just the Beckenstein-Hawking entropy. Okay. All right, but this theory turns out to be exactly, after some gauge fixing and some clever changes of variable, just exactly the theory I showed you earlier for f and phi. So you can now compute the partition function. And so finally, you get a correction to the Beckenstein-Hawking result, which is these 2 terms. The path integral of the Schwartzian gives you this log p correction with a prefactor 3/2. Now the argument of the log, it's some energy scale which depends on everything in the UV. I just put the Planck energy scale here. But the important point is there's this 3/4 coefficient, -3/4, is universal. It's a universal property of any charged black hole without supersymmetry. And it's independent of UV completion. So that's why I said in principle, this result could have been obtained in 1978 by a sufficiently smart person. But presumably nobody did it because they were very scared about the whole idea of, well, the theory is not well defined. And what's the UV completion? Can I even do this calculation? Well, that didn't scare Beckenstein and Gibbons and Hawking, so perhaps it shouldn't have scared. And in fact, even the next term beyond the Gibbons-Hawking term is universal. Okay, and all right. So now, to get this in UV complete theory for a black hole in 3 + 1 dimensions, I don't know how to do that. I mean, you could start with string theory, and then all that UV completion will do for you is fix this constant inside the law. But there's another UV completion, at least of this theory, not that theory. There's a UV completion of this theory, which is the SYK model. Okay, and so this behavior of the entropy here, the SYK model, is very generic to a charged black hole in 3 + 1 dimensions. And basically, any black hole that has an ADS2 near horizon region without supersymmetry. If you have supersymmetry, the behavior is completely different. You get exact degeneracies with BPS states, and that also there's a supersymmetric version of SYK model that has all those features, and some of that has also been worked out by, I think there's a paper by Turachi and others in ELSU who worked out the supersymmetric case also.
Subir?
All right, so yes.
I want to ask about this. Yes, precisely this slide. So this, no, that earlier slide. This with this 3/2 factor that you had in the SY case. This factor of 3/2, is it for Q is equal to 4, or it's also same as for Q is equal to 6?
It's the same for all of them.
Oh, you said that. Okay, so this. Okay, so this
well,
is.
I didn't say
so,
it, but
you didn't say it. Sorry.
It comes entirely from the SL2R symmetry. Once you have ADS2 with SL2R symmetry, the 3/2 is robust.
Okay, it simply comes from the expansion. Okay, I see. Okay, then it should be simply fixed by the SL2R invariance. So in that case.
Yeah, the 3 is the 3 generators of SL2R, something like that.
I see.
Go ahead.
Because no, I'm a bit. Yeah, so no, I just wanted to think about it. I mean, so I was so this. What I'm confused about is this. Suppose I add some higher derivative corrections to gravity, or is it known that this linear term will not change? I mean, okay, there's a universal area term and all this we know, but the temperature dependence is not qualitatively changed at this level if I add some.
So if you change the UV term, so if you change the UV behavior, either in gravity or in the SYK model,
yes,
you'll always get this entropy, but the value of gamma and U can change. The value of gamma can change, the value of U can change. Actually, even the value of S0 can change. But the 3/2 doesn't change, amazingly. S0 will change, gamma will change, U will change. So what we can compute for the case of Einstein gravity in 3+1 dimension, we can compute S0. This is the S0 term plus gamma. We can compute it exactly. This is what it is. It's in principle already there in the BeckensteinHawking paper. And if you put some higher derivative terms in gravity, I think it does change the area of the horizon a little bit. So you just have to work it out, how it changes the area of the horizon. You will get the corrections to S0 and gamma. What's almost impossible to compute is what's inside the log. In fact, that's not even computed for the SYK model.
I see.
Other than the fact
no,
that
but okay, I
power
understand this. Yeah, now I understand this log t to the power whatever that cannot change. I see. So that is probably not so surprising. It should be given dominated by the. Yeah. Okay. Sure.
Yeah.
Okay. Okay. Thanks. Yeah, I was just getting confused. Yeah.
Kind of amazing. It's the fluctuation correction that's more universal than the leading term. But even the fact it's a constant plus constant times t, that's universal, and so on.
Yeah. Thanks.
Right. I mean, if in some cases, which is the case in essentially all black holes in string theory, if some supersymmetry survives and you're doing some exact counting of BPS states, well, then the density of state doesn't look anything like this. It has a big delta function at 0 energy because the states are exactly degenerate, and what you're computing in the BPS counting has all of those number of those states. That's also about e to the n, but then the temperature dependence of the entropy at these terms is very, very different at very low temperatures. In fact, there's a gap and so on. There's no gap here.
Yes, indeed.
Okay, so I think I'm out of time. So that was all review of somewhat older work. The neo work.
So you can easily take 10 minutes more. Yeah, 10 minutes more or something, 10 or even 15.
Okay.
Okay. Yes.
All right. Great. Okay. So there's a very old problem in condensed matter, which I'll just summarize, which is trying to understand not the SYK model as such, which has all this randomness, but suppose you have a Fermi system without disorder. It has a Fermi surface, but then the interactions around the Fermi surface are so strong that you lose the existence of quasi-particles, just like the SYK model. Do we know something about that problem? So let me just quickly remind you what's the conventional Fermi surface for Fermi liquid. So if you have free electrons or free fermions, they'll occupy some states with negative energy, and there'll be a surface in momentum space, which separates the occupied states from the empty states. And this surface is has some kind of conserved volume by the Luttinger theorem. They're linearly dispersing excitations transverse to the Fermi surface. So you say that the dynamic exponent of Z equals 1. And the entropy is linear in temperature. And if you want, now in a standard conformal field theory, you'll say the entropy is T to the power D over Z. But here it doesn't work. There's some violation of hyperscaling. So it just goes linear in temperature. Okay, let me just not worry about that. All right, so what we want to do is to take this Fermi liquid and destroy the quasi-particles near the Fermi surface, the sharp excitations near the Fermi surface. And what you find is that you can destroy the quasi-particles, but you don't destroy the Fermi surface. There's still a singular surface, precisely defined singular surface in momentum space. And the simplest way to do it, one of the well-studied ways to do it, is to take your fermions and you couple them to any gauge field. Abelian, non-abelian. In fact, the behavior is very similar. So this would be a problem you might want to study, at least in 3 dimensions, for the quark-gluon plasma, where very similar theory to what I'm going to describe applies. But I'm focused on 2 dimensions. Okay, so you have some gauge coupling G of order 1, and this typically in condensed matter is some emergent gauge field. It could also be the electromagnetic field, but then the gauge coupling is so weak that the effects are negligible. Okay, so we want to understand something about the low energy limit of this theory. And the way that's usually done is, well, the way that Max Matlitsky, my student, showed most clearly it can be done, is to focus on what's called the antipolar patch theory. So you imagine you have some gauge field fluctuation wave vector Q. So this gauge field is fluctuating in this direction. It'll scatter fermions on the Fermi surface. So if you scatter the fermion here, it would go there, which is off the Fermi surface. That will cost some energy, which is linear in Q. On the other hand, if it scattered a fermion here, it will go tangent to the Fermi surface. So the energy only goes quadratically in Q. So this is a much more singular process. So for this direction of Q, you need only focus on these 2 points where the tangent to the Fermi surface is parallel to Q. Okay, so you just focus on these 2 points and expand about K0 and minus K0. And then you get this low energy theory. It looks like some gross nouveau model. It's extremely simple, but it's not relativistic. So the fermions in this direction and that direction, they're chiral fermions. They have linear dispersions in the x direction with opposite velocities, and quadratic dispersion in the y direction. There's Yukawa coupling to the vector potential. Only a single transverse component matters, and this is the Maxwell term for the vector potential. So that's the theory, and literally 1,000 papers have been written analyzing theories like this. So one of the things that's been understood is that their quasi-particles break down, and the characteristic scaling of energy versus momentum transfers to the Fermi surface is Z equals 3/2. And one way you can see it is to just do some arbitrary rescaling where you leave the kinetic terms invariant. So you have to scale x and y with this 1/2 power and tau with power Z. And you just demand that the gauge coupling be invariant. And you find that's only true at some fixed point when Z is 3/2. Okay, but what you see that when you put Z equals 3/2, that this term is irrelevant. So this disappears. So that's very much like the SYK model. The kinetic term, the d by d tau term, is unimportant at low energies. So that might suggest that there is actually a time reparamerization symmetry, and maybe something interesting is going to happen here. And so this question has kind of been open. So what people have done with this theory is, used arguments of this type in various calculations, shown that you get a Green's function with the structure. There's still a sharp Fermi surface with the real part of the self-energy changes sign, and there's omega to the 2/3 damping constant, which tells you that the lifetime of a quasi-particle, if it existed, is much shorter than its energy, and so there are no quasi-particles. But this has all been obtained in a kind of an ad hoc way, and there's many other questions you like to ask. which are not understood systematically. And if you try to do a simple large N expansion, and you put N components to psi, you find it just doesn't work. So this has been, I would say, a problem for open for 25 years. How do you do a systematic theory of the non-Fermi liquid? You have a sharp Fermi surface, and which I don't know if this really isn't clear-cut numerical evidence even for the C=3½ but there's many reasons for believing it's correct. And the entropy, in fact, goes as T to the 2/3 in this case. Okay. All right, so that's the setting up a very central problem in condensed matter, trying to understand this non-Fermi liquid. And there's many different contexts that this problem appears. I mentioned the quark-gluon plasma, there's the Hafner-Landau levels, there's various confinement transitions of spin liquids and so on. Okay, so our new work with Ilya Stulitz, Hayugo, and my former student now at Berkeley, Avishkar Patel, is the following, which is very much inspired by the SYK model and also other recent developments in quantum gravity. So the basic idea that we're going to borrow here is that it's simpler to study an ensemble of theories than to study a single theory sometimes. And why should you study an ensemble? Well, sometimes every member of the ensemble is strongly chaotic and self-averaging. But to pick out a given member is extremely hard. So you may as well focus on those properties which don't depend, which self-average, which don't depend on which member you have, and then average the ensemble. Maybe that leads to a simpler theory. Okay, so what we do is we introduce n flavors of fermions and bosons, which is the gauge field, and examples, and make the couplings between the fermions and bosons, these Yukawa-like couplings, random. But importantly, we don't introduce any spatial randomness. So momentum is still conserved, and there's still a well-defined Fermi surface. All right, so that's the basic idea, and you run with it, and it's amazing how easy it all becomes after struggling on this problem for so many years. So here's the theory I just showed you. There's a few additional phase factors. It depends on the detail, but you introduce this G alpha beta gamma, the coupling between the boson and the fermions, and you make it a random number in flavor space. So each member of this ensemble is a perfectly legitimate non-Fermi liquid with some peculiar symmetry, with some set of coupling constants, but you expect some universal behavior near the Fermi surface, which shouldn't depend on which set of G alpha beta you choose. So you choose some random set, and then you average over them. Okay. So the whole analysis is actually very, very similar to the SYK model. By same set of tricks, you get a path integral, which is a formally exact representation of this ensemble with a G sigma action, which is now an action of fields that are not just bilocal in time, but are bilocal in space-time. This is a space-time coordinate. So it's more complicated, but formally has the same structure. So from this, you can now look at the saddle point. You can now turn the crank and do everything we've done for the SYK model. You can look at the saddle point. You can look at fluctuations about the saddle point. You can look for instabilities with broken symmetries, the way Klebanov and others have been looking for the SYK model. And we've done all of that. And there's much more to do. And some of it is described in this paper with Ilya, Hayu, and Avishkar. So I think let me just flash a few results. For example, if the saddle point equations look like this, these now have both space and time and frequencies and momenta, but they again have a very similar SYK-like structure with the self-energy depending on some powers of the Green's function in real space and time. Not easy to solve, but in the scaling limit, in fact, you can solve these equations exactly. This is the solution. Now, instead of getting square root of omega, you get omega to the 2/3, and you can get all this. This type of function was gamma functions, and now this is a more complicated function. You can actually
Subir?
solve the saddle point. Yes.
Is there an easy way to understand the K independence, this independence of K of this self energy that you're getting here?
Yes. Let's see. So it comes basically from the momentum integration. Can you see my? I can write it here.
Unfortunately, this will come out very tiny. Only if you unshare.
Let me.
Yeah. Now okay. It will be perfect. Yeah.
So now, if you focus in on my on the speaker, you can see it. Yeah. So you often get you get some integral. So you have some. So here's the Fermi surface. This is Kx. Let's call this Kx. And so you get integrals like dkx of various terms, and the dispersion depends linearly on kx. You have I omega minus kx minus sigma of omega. Okay, so what happens when you do this integral, and there's all kinds of k dependencies everywhere, but when you do the integral over kx, the only thing you need to know whether the pole is in the upper half plane or the lower half plane. And so when you do the integral, all of those complicated dependencies drop out. So the things amazingly simplify.
Yeah, but a stupid thing maybe, Justin, but typically in many of these field theory cases, you are supposed to do the omega integral first and then the K integral. Okay, you can assume that correct. The integrals can be exchanged, but.
If you want the full answer, that's correct. But if you want the singular, if you're satisfied with the singular part, it doesn't matter which order you do it. So you do it the easier way. The singular part is independent of that. But if you want the full, including the real part, and if you want the constant additional non-universal things that depends on the full Fermi surface, not just on the patch, then you're right. But if you're interested only in the patch theory, you can. It doesn't matter which way.
Okay, I understand, because you're focusing on the patch only. Okay, thanks.
Yeah. So this is actually quite a important point, and so I think I'm writing a review article where this is going to be explained in some detail. Okay, so now I have to share again. I'm almost done. Let's see. You can see my screen now, right? Okay. All right, so this is the saddle point, and we can do various things. You can now look at fluctuations about the saddle point. So what we found for the SYK model, that when you had this time parameterization symmetry, that led to a very singular effects with the zero mode and the Schwartzian theory, which actually led to breakdown of scaling at order 1/n with these logs and so on. Well, it turns out that doesn't happen here because of some interplay between the spatial and the time structure. This is where the fact that there is a momentum does become important. So this saddle point is actually more stable than in the SYK model. There's no soft mode that you have to worry about. Then you can also look at 1/n corrections to this bilocal field theory, and they have, at least formally, diagrammatically, they look very similar to the graphs you get for the SYK model. These kind of things have been studied by Rosenhaus and Gross, I think, and also Kitev and so. This is the way you write them in the bilocal theory, and this is the way you write them in terms of the original theory. So they're really made up of sheets. There's different kind of surfaces that you have to sum over, and so this is starting to look like a string theory. But we don't, these are very hard graphs to evaluate. We haven't actually evaluated them. We can just list them, and that's about it. At 1/n, there are two graphs. There's this graph and that graph, basically. But this is extremely hard to evaluate. And in higher orders, there'll be different topologies and so on. So it's at least as difficult as string theory, probably even more, because there's very little symmetry here. Anyway, but at least there is in principle a well-defined expansion about a saddle point. And the saddle point we can now study very systematically. We can also look at instabilities. This is the exactly type of equations I showed you earlier for the higher operators. And sure enough, you find some simple operators like the density and the energy. And then you can find pairing instabilities and 2kF operators with irrational scaling dimensions by solving a very similar type of equation. And this is all in our paper. you have to solve some of these equations numerically, but that can be done. All right, so I conclude then. So the SYK model is a solvable model without quasi-particle excitations, with exhibiting thermalization and chaos in a Planckian time. And this time is independent of microscopic energy scales. So as such, it is, similar to other strongly coupled theories of great interest in condensed matter, but also solvable, and that's been very, very helpful. It has the low energy limit of the SYK model is theory of 2D quantum gravity on ADS2. And so this theory has a boundary graviton, which is also present for the SYK model. And this boundary graviton leads to, well, this is the saddle point, n equals infinity correction to the spin susceptibility. In my talk on Wednesday at ICTS, I will also talk about a more realistic model called the tandem TJ model. And there, in fact, the same boundary graviton is also the hero of the story because it gives this famous linear interior resistivity. And it also leads to the first correction to the Beckenstein-Hawking result, which is universal for any charged black hole with the ADS2 near horizon. And I just gave you a little flavor of taking this idea of ensemble averaging theories and really getting a fair bit of mileage and on an old problem, which is the problem of Fermi surface coupled to gauge fields. So thank you.
Thanks, Subir, for this wonderful talk. And thanks also for telling about your new results on this critical Fermi surface. So it's time to take questions now.
Can I ask something, this is Raj?
Sure.
Yeah, sure.
Yeah. So one thing is that your time reparameterized soft mode action, which you had written down. You said that you can calculate the density of states from here. So what is the calculation you have to do to get the density of state, the sinh hyperbolic thing in that case?
Yeah.
So do you have to calculate the the sub-zero mode solution and then put that back in somehow to calculate the density of states?
No, so it's just, it's an inverse Laplace transform. So,
okay.
So you compute the partition function. So the partition function Z, which is a function of beta, is the path integral over the Schwarzschian, df e to the minus s Schwarzschian of f. Okay, so you compute this, whatever it is, as a function of beta, but this is also equal to 0 to infinity dE density of states times e to the minus beta e.
Okay.
So once you know Z of beta, then you can, in principle, get D of E. But you can also see this kind of an ill-posed problem because in inverse Laplace transforms are very ill-posed. That is, if you make a tiny error in Z of beta, it'll lead to huge error. It allows huge errors in D of E. But in this case, since you can do this exactly, the point is that since the Schwarzschian path integral can be done exactly without corrections, then the inverse Laplace transform is reliable. Okay. If you didn't know it exactly, then you couldn't believe the inverse Laplace transform. Because any higher order, something that's higher, in other words, if you have some expansion for this and you ignore the higher order terms, well, for Z of beta, the higher order terms are very small. But that doesn't mean the higher order terms will be very small for D of E.
D of E, yeah.
Yeah, something that's very small here could lead to a huge effect here. So it's very important that you get the full Z of beta to figure out D of E. It's the usual problem of analytic continuation from imaginary time to real time. It's not easy to do in principle, but this is one of the cases where you can do it. Yeah, this wasn't done by me. It was done by Stanford and Witten and Altland and Maldacena, Stanford, a lot of people. Yeah.
Subir, I have a question about the critical Fermi surface at large N. So,
yeah,
is there some bosonized version of the theory one can study?
Yeah, people have tried, but it doesn't go anywhere as far as I can tell. No, yeah. I mean, I would say the bosonized version is the DSigma theory I showed you. That is the bosonized version. The DSigma theory, that's bosonic. That is I think the correct way to think about it.
But it's very non-local in terms of.
Yes.
Yeah. So somehow
well,
there.
Yeah.
It's non-local, but as you said, if it is k independent, then things change. If it's non-local only in time, not in space, for some reason, and now this is
right. So there have been various attempts to bosonize the Fermi surface. Well, you can. Yeah. So the problem is this. You can see my screen, right?
yes.
Yeah. So it's over here. So the problem is that if you only care about the dispersion tangent to the Fermi surface, normal to the Fermi surface, then you have just a 1D chiral fermion, okay? Because you don't care about the y direction. So you can take each point of the Fermi surface and think of it as a 1D chiral fermion and bosonize it. That's basically, there's again 100 papers that do that. Now for a Fermi liquid, that works. That perfectly works because that's a good approximation to a Fermi liquid, that the dispersion is only normal to the Fermi surface. So you can have a bosonized theory of the Fermi surface when you have quasi-particles. However, for this thing, you cannot ignore the quadratic dispersion. The fact it's quadratic to this del y squared cannot be ignored. It actually controls everything. Okay, and that's very hard to include in bosonization. I think, if I may recall, there was a paper by Fradkin who tried to include this, but I don't believe it really led to, as far as I know, I may be misspoken, but I'm not aware of, some new results that comes out of that, something we'll. On the other hand, I would say the correct way to bosonize it today, in my opinion, here's the bosonic theory, the DSigma theory, and you get it only after this average ensemble average. That's what you should do.
I see. So another related question is that at this Fermi, although the Fermi surface is not well defined, but sorry, what I mean to say that you don't have quasi-particles, but still at k is equal, you had still at omega is equal to 0, you still have a sharp Fermi surface, a pole in
correct,
k, right?
Correct.
And
yeah, this theory has all of that.
So in this sense, one can have some kind of notion of a shape, and so there is always some speculation that the shape of the Fermi surface could be understood as an emergent mode or something like that. Is the easy way to see in this large n limit we can make it precise?
Yeah, so there's first of all, there is a sharp Fermi surface, and its volume is invariant. That's the Luttinger theorem, and that's true even in this theory. That's true even for non-Fermi liquids, that there's a Luttinger theorem preserves the volume. But then you can talk about other types of distortion, volume preserving distortions, which are fluctuations in the Fermi surface. Yeah, and I think you can do that, and people have, I think Damson had some paper like that for Fermi liquid, some limits.
I mean, my question is essentially whether is in the patch theory that you have this with only coupling antipode, does it get suppressed or somehow it gets, you don't see this if you take such approximations?
Well, there's two things here. I mean, this DSigma theory can be written without the patch analysis. You only need the patch analysis if you want to solve the saddle point equation exactly. You can write down the analog of this without the patch, which is written in our paper. In fact, we solved the full theory without the patch numerically. But if you want an analytic solution of the patch of the saddle point equation, then you do have to take the patch limit. And the full solution, which we did numerically, agrees with this. So we found that was one of the reasons for doing the full solution, to avoid the patch approximation, at least at the saddle point level. And yeah. Now, if you want to do 1/n corrections, that's hard enough in the patch approximation. But in principle, it can be done without the patch approximation. At least it's there. You can write down the integrals you have to evaluate and the integral equations you have to solve, but it would have to be done by computer, I'm sure.
Nice.
Hi, you made some comment about the lack of reparameterization symmetry, right? Could you repeat that?
Yes. Yeah. So what happens is, All right, so there is this, formally, there seems to be a reparameterization symmetry here, okay, where you rescale time. But you also have to rescale space by some factor of f of tau. And because you rescale space, you get some extra Q dependence appearing in the zero mode equation. So the mode is actually not zero mode. I mean, there's the time representation mode mixes with, can exist at different momenta, and there is a mass there which depends on momentum, if you wish. So there is no zero mode. In fact, the time representation mode just becomes it becomes essentially the energy fluctuation, which is just diffusive. We know what the structure of energy fluctuations is in a non-Fermi liquid. So you don't get anything new coming out of it. Yeah. So I wish I had a little more detail, but this is actually discussed in great detail in our paper, in this paper.
More questions?
Okay. All right.
Okay. So if you can also ask Subir more questions at the ICTS talk, it's probably related. I think there's some. Okay, so
yeah, but
so thanks, Subir, again. So
sure.
Thank you.
Thanks. Nice to see you all.
Yeah.
Thank you.
Yeah, thank you, Subir.